Well, good afternoon, everyone, and welcome to this distinguished lecture, which is being hosted jointly by the Waterloo Institute for Nanotechnology and the Waterloo Institute for Sustainable Energy. In fact, this is the first time that WIN and WISE have collaborated by sharing a distinguished lecture. And we certainly hope that there will be many more of these in the years ahead, since we both of our institutes share not only common interests, but also faculty who are members of both. So welcome to members of WIN, welcome to members of WISE. And I think it's particularly appropriate that our first joint speaker is Dr. Chidabaram, an eminent physicist, metallurgist, and neutron crystallographer who has contributed significantly to science itself and to energy policy in India as the principal scientific advisor to the government of India, as chairman of the Scientific Advisory Committee to the Cabinet, and as chairman of the Atomic Energy Commission from 1993 to 2000. Dr. Chidabaram completed his BSc and MSc in physics at the University of Madras in Chennai, and then his PhD in nuclear physics at the Indian Institute for Science in Bangalore, working on nuclear magnetic resonance. He joined the Baba Atomic Energy Research Center, BARC as it's called, in 1962, becoming the director in 1990. And the research groups which he established at BARC in high-pressure physics and neutron crystallography are still regarded as among the best in the world. On the energy side of things, he became chairman of the Atomic Energy Commission in 1993 and chaired the Board of Governors of the International Atomic Energy Agency for 1994-95. In 2008, the International Atomic Energy Agency invited him to be a member of a commission of eminent persons to make recommendations on long-term priorities to the board. He is also a member of the Prime Minister's Council on Climate Change. Dr. Chidabaram has many awards, including the Padma Vibhushan, India's second highest civilian honor, and has more than 20 honorary degrees from Indian and foreign universities. He also serves as the chairman of the Board of Governors of IIT Madras, to fulfill the whole picture. He's the chancellor of the University of Hyderabad. So please welcome our distinguished speaker, Dr. Chidabaram, who will speak on energy technologies, energy security, and climate change.
Thank you, Professor Kati, for the kind introduction. It's a privilege to be here and to talk in this lecture series, and I'm very grateful to Professor Arthur Kati and Dr. Jatin Natwani for this invitation. And of course, during the 2 days, I also had the opportunity to talk to many distinguished scientists here, various aspects, nanotechnology, solar energy, energy issues, smart grids, and a variety of issues. See, the quality of life of a country or the individuals in that country depends on the availability of energy, availability of electricity, which is of course the most convenient form of energy. And people in already developed countries, because they want to retain the high quality of life, they want to sustain their energy consumption, if not increase it further. And people in developing countries who aspire to become developed countries want to increase the level of consumption of electricity, production of electricity. Then of course they want energy security, not just reach there, but stay there. And this energy security is now being threatened by this potential global climate change threat. Most people are convinced that global warming has started and has been caused by anthropogenic greenhouse gas emissions. Of course, there are skeptics, not as there are no skeptics. But global warming, I think, most of the serious scientists think that this is a matter of serious concern. And on this, they have no doubt about what the IPCC has said, Intergovernmental Planet and Climate Change, though they did goof up on the Himalayan glacier melting. That's where it caused a bit of a problem for the IPCC. Now there are three aspects of climate change threat. High resolution modeling, particularly of areas which we consider vulnerable, most vulnerable. Then mitigating technologies. What are those technologies which are likely to mitigate the climate change threat? And then, since it is already upon us and probably will get worse, what are the adaptation strategies? Particularly, this is likely to affect the countries in the southern hemisphere more, the so-called developing countries. But here the focus in my talk is going to be on mitigating technologies as far as the climate change threat is concerned. Now, I've been saying this for now 20 years, that the Human Development Index, which the United Nations defines, they use three parameters to define it: per capita GDP, life expectancy at birth, and adult literacy. I've been saying you need only two parameters: per capita, electricity consumption, and female literacy. I prefer female literacy to adult literacy because it's a measure not only of literacy but also of equity and justice in that society. And you can plot it, you can plot infant mortality, you can plot birth rate against female literacy. Is a very strong correlation. The higher the female literacy, the lower is the birth rate, the lower is the infant mortality. The other two parameters which the United Nations uses, per capita GDP and life expectancy at birth, can both be replaced by just one parameter: per capita electricity consumption. Per capita GDP obviously is monotonically related to per capita electricity consumption. More electricity, more is the goods you manufacture, more is your GDP. It's more tricky to talk about health parameters, but if you introduce any energy giving system, any electricity producing system, part will go to industry, part will go for urban consumption, but a part also goes to small towns and villages. They have better drinking water, better sanitation, better primary health care, and all these have an impact on health parameters, particularly the ultimate health parameter, which is life expectancy at birth. That is why I replace both per capita GDP and life expectancy at birth by just one parameter, which is per capita electricity consumption. And all developing countries, this per capita electricity consumption has to go up manifold before they can hope to have a high quality of life. In the case of India, the electricity production has to go to over 1 million megawatts. We are hoping by 2050, India will be a developed country in the fullest sense of the term. And by that time, you must be something like 1 million megawatt plus. We are talking about a very fairly high growth rate for India, GDP growth rate 8%. Prime Minister thinks even double digit is possible. If you want to sustain that till 2050, and services will take you only that far, not too far, manufacturing has to come in, which is energy intensive, then again you get the same answer, 1 million megawatt plus. And take it from me, even if the climate change threat was not there, there is not enough fossil fuel in the world for us to reach that kind of consumption. That's why nuclear becomes very important. This I replotted very recently for this talk. So the data you can see is 2000 World Bank 2010 data. I plotted the Human Development Index against per capita electricity consumption. See, I made it logarithmic scale. If I don't make it logarithmic, developing countries will disappear near the origin. So I stretch the scale by going logarithmic. And this is an S-shaped curve. This is because a human born in the poorest parts of the world will hang around for about 40 years because the major epidemics have gone. And at the other end, the human system begins to fail at about 80 odd years on an average. This is the main reason it's an S-shaped curve. And India, after independence in 1947, is rapidly climbing. As you can see, the numbers I have given here, they indicate female literacy. And female literacy is higher, you stand out above the curve, and corresponding to this, the female literacy is lower, you tend to go below the curve. That's why female literacy is so important. Even in India, I can plot a similar curve for India. And Kerala, which has got near 90 plus, will stand well above this curve. So no country can become a developed country unless it is near 100% literate without gender discrimination. And in this case, of course, unless you take your per capita electricity consumption way above what is now available for these countries. Now, this is the commission which Professor Carty mentioned. I was a member of this, and from Canada it was Louise Fréchette. Louise Fréchette was a member of the commission. Of course, it's a kind of a mixed commission. We had scientists, we had politicians, we had economists, and it was a clear statement that expanded use of nuclear technologies offers immense potential to meet important development needs. And they considered, or we considered, the two of the 21st century's greatest challenges: energy demand and climate change threat. And those countries which wanted, because there are some who are anti, in my opinion, every country should want nuclear. Major opportunities for expansion of nuclear energy in those countries that choose to have it. Because the theme of the committee was, the mandate was to talk about the role of IAEA. International Atomic Energy Agency is the main body which takes care of nuclear energy. It's the United Nations body. Now, there is very little doubt that a nuclear renaissance is now on, and it has, of course, geographical dimensions. There are countries which are freshly starting a nuclear power program. I was a meeting in Abu Dhabi, and Abu Dhabi is going to have a nuclear power plant being built by the South Koreans. So the question was, why should Abu Dhabi or United Arab Emirates, which is floating on oil, go for nuclear? Their attitude is that we cannot allow our entire economy to depend on just one source of energy or one natural resource, which is oil. They want to diversify it, and they also want to make sure that the oil they have lasts a longer time than it would do otherwise. Somebody there asked me a question, why should Abu Dhabi? I said, if burning oil and creating carbon dioxide is a problem for the world, it doesn't matter whether you own the oil or you buy the oil. Everybody has to cut down on fossil fuel. Now there are countries which have had a continuous and sustained growth at various velocities, India one among them, of the nuclear power program, and are now accelerating growth for reasons of energy security and because of this potential climate change threat. It's very clear you can grow very fast. We have got examples, I'll show you in a slide in a moment. Countries which had a very rapid growth, but we have stagnated in the last couple of decades, partly because of Chernobyl and 3 Mile Island accidents. But now they are restarting the growth. See, this is United States. Between 70 and 90, they reached to 100,000 megawatts. Thereafter, they have been, partly because they have gone in for efficiency. France, 80% of France's energy comes from nuclear electricity consumption. They also grew very fast, but are growing but at a reduced velocity. This is Canada. Canada was a pioneer in nuclear. Until about 1995, they're growing very fast, but they're more or less flat now. India, China, and South Korea. This is what I meant. These three countries are growing. Fastest is Korea, South Korea, then China, and then now India. And India now hopes, because of changes in the nuclear supplier group guidelines, kind of problems which South Korea and China did not have till recently, that we hope to grow faster now. And this is how it evolved. Rajasthan 1 and 2, this was built with Canadian collaboration. Then in the 70s, collaboration with Canada fell off. And then there was a period when we had to indigenize, standardize, consolidate, and commercialize. And now that was 220 megawatts. Rajasthan reactors built with Canadian collaboration, 220 megawatts. Now India builds 540, and all the future ones will be 700 megawatts. And the gestation period is comparable to international. From the first pour of concrete to the first day of criticality, date of criticality, it's about 5 years now. Because it is all done by Indian industry, but very big companies, Bharat Heavy Electricals, Larsen and Toubro, Walchandnagar Industries, who can build all the components which are needed for nuclear power plants. And as we say, all our future projects will be based on these heavy water reactors, which is the starting from CANDU, which has horizontal tubes, which use natural uranium, heavy water as moderator, heavy water as coolant. That will be for the future reactor. And it turns out that what we build here in terms of capital cost per kilowatt is among the lowest in the world. $1,300 or $1.3 million per megawatt. And by 2016, and it is competitive with other electricity generating technologies in terms of tariff. The way the Planning Commission of India calculates this, not in terms of capital cost, obviously it is more expensive to build a reactor than a boiler burning coal, but they calculate in terms of the unit energy cost at the same location. Pithead coal will beat anybody. But as you move further away from the coal pithead, to the cost of coal you have to add the transportation cost. And at about 700, 800 kilometers they become comparable with coal generated. These are the plans. We want to reach nuclear capacity of 63,000 megawatts, around about that. Nobody can say exact figure. 2032, this is the projection, out of which light water reactors will be 40,000 megawatts, and the rest will come from PSWRs mostly, and also fast breeder reactors. And then of course by that time I'm sure we will have light water reactors which are our own design, and we hope to be ready to export these kind of reactors. Small countries need only small capacity reactors. Fast breeder reactors are reactors which breed more fuel than they consume. Because in every fission reaction you get more than 2 or 3 neutrons. One is needed for the chain reaction. And suppose more than one becomes available for breeding new fuel, then you get it becomes a breeder. That is, you breed more fuel than you consume. And why it is important, what we mean by closing the nuclear fuel cycle, is the same uranium will give you 50 times more power if you close the cycle with plutonium. 600 times more power if you close the cycle with thorium. Uranium-238 in a reactor gets converted to plutonium-239. Thorium-232 gets converted to uranium-233. So these are all fissile materials which undergo fission in nuclear reactors. Now this is the three-stage Indian program. Natural uranium oxide fuel, that's the first stage. Heavy water reactors. Any reactors we import will become part of the first stage. And in this fuel you produce plutonium. If you cut open the spent fuel, take out the plutonium and build fast breeder reactors, that is called closing the nuclear fuel cycle. Of course, some people may choose to put away the spent fuel as so-called waste, that's called the open cycle. But the good thing is that plutonium is not running away anywhere, it is there, because the half-life of plutonium is 24,000 years, and one can take out at a future date and put it back into new kinds of reactors. Third stage, these reactors, the fast breeder reactors, will have thorium as blankets, which will get converted to uranium-233. In third stage, it will come some decades from now, will depend upon this kind of reactors. We have had a fast breeder test reactor, 40 megawatt, which has worked well for 25 years. In fact, 10 days back, we celebrated the silver jubilee of this reactor. It used a new kind of fuel, plutonium-uranium carbide, which is a very efficient fuel, though making the fuel is a little more difficult. So the prototype fast breeder that we are building, 500 megawatt, will have oxide fuel, but finally, if you want to breed at a high ratio, you have to go to metallic fuels. So all these, of course, you can have loops inside these reactors, which test out whatever fuel that you want to try in future reactors. And it has to be backed up by of course this shows the construction of this 500 megawatt reactor. They have built a 100% simulator of the control room in this Indira Gandhi Center. So the operators who operate these reactors can be shown normally how it operates, or if unusual conditions arise, how they react to it, just like aircrafts. And it required a large amount of R&D, like pool hydraulics, thermal hydraulics, or grain boundary engineering, or how to inspect it. You know, once the thing gets radioactive, you can't take things out. You have to do in-service inspection. And then, of course, if there is a core disruptive accident, all those simulations, all those calculations are now possible. And this is how the prototype fast breeder reactor has been designed. Now, see, nuclear is now recognized as a mitigating technology in the context of the climate change threat. And the Intergovernmental Panel on Climate Change has many scenarios which you see here, and there are scenarios in which nuclear plays a major role, and I'm showing you one of those scenarios. The purple curve that you see, there's about 380 gigawatt of 380,000 megawatts of nuclear power in the world today. And the purple curve that you see there is the way up to about 2070. This is how they expect the contribution of nuclear to grow. Today, a reactor built lifetime is about 60 years. Thought it would be 30 years, but can last for 60 years from experience now of the various regulatory boards. And there is a certain amount of proven reserves of uranium in the world. Proven reserves. Of course, we can be optimistic that more uranium will be discovered. But if you take only the proven reserves and then say, if I build a reactor, I must put away enough uranium for its lifetime, 100 gigawatt is all that you can get from proven reserves of global reserves of uranium. It's a paper we wrote about 3 years back, 2007. But this is what is needed. This is all you can reach if you follow an open fuel cycle. That is, if you don't recycle the plutonium. But if you want to go like that or anything like that, any one of those scenarios, you have to close the nuclear fuel cycle. That is why I say that if you want nuclear to be a sustainable mitigating technology, sustainable, in the context of the climate change threat, you have to close the nuclear fuel cycle. Now, see, it's a very interesting study because I'm going to mention it again, that when we collaborate with countries, whether it's United States or Canada, I tell my friends that you shouldn't look at India just as a market, because we have got complementary capabilities and we should work together, manufacture the components and look for global markets. And it is in this context I'm showing you this slide that in the last couple of decades, the services sector has created a lot of wealth for India, particularly the IT services sector. But that is short term. But if you want any country, including India, it has to grow, continue to grow, it has to rely on the manufacturing sector. And this is a study done by Deloitte and the US Council on Competitiveness. It's the latest one which has come, I don't know, sometime in September, I think. What they say is they have ranked India as second after China. And one of the factors which drives this is what this group calls talent-driven innovation. Now I must distinguish research and innovation. Research is generating new knowledge. Innovation is deriving economic value, strategic value, or societal benefit from knowledge. That's what innovation is about. And the feeling is, of course, one can talk of product innovation, process innovation, and also design innovation in many cases. Now, there is already a great amount of manufacturing competence in the nuclear sector, and hoping that as we collaborate with friendly countries, we can have joint ventures, we can do joint development of more advanced reactors and so on. Now, of course, nuclear is not, there are other possibilities. There are other reactions like spallation reaction. Suppose you take a 1 GeV proton and make it collide with a high Z material, uranium or lead or tungsten. Neutrons kind of boil off from it. This is called spallation. And tens of neutrons will come from each reaction. And suppose you surround it with the subcritical reactor. In reactors there is a factor which is called the multiplication factor. You count the population of neutrons in one generation, you divide it by the population of neutrons in the previous generation, and this ratio is called K. In a steadily operating reactor, whether it operates 20 watts or 200 megawatts or 1000 megawatts, K is 1, more or less 1. Because it's a steadily operating reactor, the population of neutrons remains the same. If K is less than 1, that means the reactor is shutting down. Successive generations, population of neutrons is going down. And that is how the reactor is shut down, K is less than 1. But it is still a multiplying system. You introduce a neutron, the neutron population gets multiplied. Roughly speaking, by something like 1 by 1 minus K. 1 by 1 minus K. Suppose K was 0.9, the population will get multiplied by 10. But 9.5 get multiplied by 20. So what they've done is, if you take a subcritical reactor, which is a multiplying system, and introduce into it a source of neutrons produced by spallation reaction, by a proton accelerator. This is a possibility, because one has to build accelerators which are a very high current, because it's a neutron source. Livermore is now thinking of, even neutrons produced by inertial confinement fusion, laser-induced fusion, as a source of neutrons which can be put into they have an experiment which they call LIFE, laser-induced fusion experiment. See, if you go to nuclei like uranium, when a neutron enters, the thing breaks up. It's fission. But at the lower end of the periodic table, isotopes of hydrogen tend to fuse together. And when they fuse together, and you look at the resulting atoms, resulting nuclei, there is again a mass deficit. E is equal to mc squared applies and energy is released. Heavy isotopes of hydrogen, D or T, when they get together, that is how they look for fusion. And that fusion cross-section is a function of temperature, because these are two nuclei which repel each other, electrostatic forces. If you want to bring them close to one another, you must go on increasing the temperature, so that by sheer kinetic energy they will come near each other. And for this fusion cross-section to be significant, the temperature has to be in the region of 50 to 100 million degrees, 50 to 100 billion. Obviously, there is no question of any material. So either you confine it by a magnetic field or a set of magnetic fields. This is how magnetic confinement fusion, tokamak and all that. Or you do it so fast that you don't need confinement. This is what you mean by confinement by inertia, inertial confinement. In the Livermore experiment, they take a pellet of DNT or DND, hit it from 192, hit it by 192 laser beams, and then you send a shock wave inside. And as the shock wave goes in, not only does it increase the density, it also takes the center to ignition temperature. This is how this is done. And Livermore people now think that you can use this as an amplifier, energy amplifier, neutron multiplier. The other thing which may come to pass before fusion in full strength is, of course, eventually as reactors, but you can do energy amplification, as I have said, or you can do it as hybrid, use it as for breeding. See, a fission reaction is energy rich. For every reaction you get very large amount of energy, 200 MeV. Fusion reaction is neutron rich, 17 MeV. So you get an order of magnitude more energy from a fission reaction than from a fusion reaction. So the clever way to do it is take a fusion neutron, breed fissile material. That is what is meant by hybrid. Start with fusion, end up with fission. And this is a distinct possibility in the intermediate term. ITER is the biggest experiment, international experiment, thermonuclear experimental reactor. India is now a full member of that. This is being built in Kadarash, 500 megawatt, just an experimental. What has happened so far in fusion is to achieve scientific break-even. Whatever energy you have put in, equal energy has come out. But that is not technology. If you want it as a technology, 10 times more power must come out than what you have put in. And that is what this will prove, apart from the confinement times, Lawson's criterion and all that. And all countries, and India as a member is going to contribute some of these items. Every country's contribution is not in cash, except French alone, I guess, but in kind, like this cryostats or vacuum vessel pressure systems and so on. And we have a steady state tokamak thing being built, which is one of the important experiments whose inputs will be valuable when they design the ITER. Now, you see, now the way we do research, or for the matter, the way we do teaching, can be enhanced by using electronic connectivity. And we are building this national knowledge network, which is whose topology is shown here. And every one of these main nodes will be connected with 100% redundancy to ensure high reliability. And the first phase is over. Now we are going in for the full phase. And we also are connecting this to international networks. Europeans are the ones, because we were already collaborating on the Large Hadron Collider. So European, because massive data is going to come out of the Large Hadron Collider after it has been built. And NKN is connected to GIANT, which is there. Each country in Europe has its own optical fiber network, but the overarching network is GIANT. And we are connected to the United States with Gloria just now. And I want, we are very keen that the National Knowledge Network and the Canadian network, which is called Canary should be connected. Of course, ICT, I think you should note this. You see, there is a group called Climate Group, of which several states, I noticed, several provinces in Canada are members. It's called the Smart 2020 report. And they feel ICT can play a major role in encouraging a low-carbon urban society. Low-carbon urban society. Of course, ICT also helps in rural. And of course, these are all numbers. Each group gives its own numbers. And there are smart meters which are already there, smart grids. One has to see how it works. And smart buildings, smart cities, to the extent possible, how one can. And every time you have a teleconference, you replace a physical conference with a teleconference. Well, that's a green technology in the sense that you don't spend that much of aviation fuel, provided you have this kind of optical fiber networks which can give you high resolution teleconferencing with a very, very low latency. Now this is the IPCC assessment, fourth assessment of and I think there is very little doubt that the global warming is unequivocal, and that these numbers are fairly well settled. You can see the range of warming they have given as, I think 1.1 is impossible, because countries are not cutting down the carbon dioxide emissions significantly. Upper end, if the rich countries don't change their lifestyles, you may hit the upper bound. And then of course they predict a corresponding sea level rise. There are also modeling uncertainties, the modeling, very complex modeling required for this. And also the data from developing countries has not been inputted. Now of course one of the things which all national action plans on climate change are doing is to collect more reliable data from, including India. We are trying to get better data from this. Now, because of this pressure, because of these skeptics, the Royal Society London very recently has come out, which is I think a very, I'm reproducing it here because I think it is a very scientific statement. Of course, it by and large agrees with the global warming from the IPCC report. But it says that there can be variations, of course, from climate forcing or radiative forcing, the amount of radiation which falls from on the earth and how much it is returned. And there can also be variations due to interactions which we don't fully understand yet. For example, in the oceans and the atmosphere, referred to as internal climate variability. But they agree with this 0.8 plus or minus 2. But they feel that satellite measurements, many other measurements are not of the same quality. Satellite, of course, is only for a very brief period in the last few decades. And they say we must study these additional mechanisms, the response of the carbon cycle, as they say, which is really the exchange of carbon between the atmosphere, oceans, soils and plants to climate change. Enhanced melting, on which there has been controversies, and in order to predict how much will it rise, because one of the things is that low-lying island states will be very badly affected. Then of course there is always a possibility that new science may emerge which we have not factored in relating to climate change or climate itself. First we must understand climate before we can talk of climate change. But this is for sure that there are, if you take relative carbon emissions, coal, if you take integrated gasification, combined cycle, natural gas, nuclear, hydro, renewables, of course they emit very little carbon dioxide. That is why if you are to look at the mitigating technologies in the context of the climate change threat, nuclear, renewables, hydro, both large hydro, micro hydro, also efficiency. For every megawatt that you produce, you must emit the minimum of carbon dioxide. And for every megawatt that you have already produced, you must use it with the best efficiency. That is why in the National Action Plan on Climate Change of the Government of India, and there are similar things brought out by various countries, there are 8 major missions. There is a national solar mission. We want to reach 20,000 megawatt by 2020. National mission on enhanced energy efficiency. They are getting very tight about this in terms of appliances and all that. There are things on sustainable habitat, on water mission. Water will be badly affected. Then of course the Himalayan ecosystem, apart from the glacier melting. Green India, which will be for putting up much improving the forest cover. Sustainable agriculture, particularly if the temperature goes up and wheat is to be affected, should we produce through plant genomics new varieties which are resistant to thermal stresses or any other related stresses which it produces. Then of course an overarching strategic knowledge mission for climate change. You will see nuclear is not here because nuclear, the Department of Atomic Energy itself is called a mission-oriented agency. Its only mandate is to produce nuclear power plants and some other related things. Now we are thinking of a 9th mission on clean coal or clean carbon or relatively cleaner carbon technologies. Solar photovoltaics, of course we have to concentrate on improve solar cell efficiency. Silicon is going to stay a long time, and can we increase it? People who work in this field are confident that they can increase the solar cell efficiency, bring down the cost. Thin films, new materials. Solar thermal will have to develop. Then there's a lot of interest people I met here on storage, because unfortunately sun is not there 24/7. So you have to store it, or at the time sun is not there, you must hybridize it with some other kind of power production. And then this romantic idea of putting a kilometers dimension solar panel into a geocentric orbit where the sun comes all the time, produce a gigawatt of power and send it down by microwaves. Well, it has been in the air for 3-4 decades now, and there are some people who think one day it will come to pass, which a lot of new technologies will have to be developed for this, and safe technologies. We are going to set up a National Center for Photovoltaic Research and Education at IIT Bombay. Government is pushing for R&D in this area. They have a nanoelectronic center there, so that a lot of common scientific areas are there. See, this is the electricity generation in Canada. It's from the Canadian Nuclear Association. As you can see, Canada is rich in all kinds of resources, natural resources, including hydro. Hydro is about more than 60%. And that's why, in spite of Canada being a pioneer in nuclear, CANDU reactors, heavy water reactors, natural uranium, wonderful type of reactor. Now, of course, they have got more advanced CANDU type reactors. It has stayed at about the same. And then the other kinds of. India, it is heavily coal. See, our total production is about 160,000 megawatts, and more than half of it is coming from coal. Among renewables, it's substantially wind. Solar is a small component. Hydro, you are asking for percentage hydro. It's about 25%. I was thinking 30%. Nuclear, and then diesel and gas and all that. That is why this 9th mission on, see, however much we talk of nuclear and renewables and all that, next 20, 30 years, it is going to be mostly by burning coal, the power production. So, the higher the temperature at which you can produce the steam, higher the temperature and the corresponding pressure, higher the efficiency of the power plant. So from normal to supercritical to ultra supercritical, we want to go straight to advanced ultra supercritical. And this kind of plant has not yet been built at about, with all the features. Carbon capture and value addition. Carbon dioxide is a pretty stable molecule. But even if people have thought about it, value addition, but the thing is, the amount of carbon dioxide that you produce in power plants, there is not enough demand for the value-added products. Carbon capture and storage, that is, take away the carbon dioxide, and this work going on here. Professor Yuri Leonenko, I saw. Yes, and Sask Power is also doing it. Of course, there what they are thinking of is a very clever method. Take out the carbon dioxide, compress it, and use it for rock fracturing in oil reservoirs, so that you stimulate the reservoir. So, those are all possibilities. Americans had this Future Gen project, but once they stopped the subsidy, I think the interest of the companies has come down. But this is surely a very important R&D area, that if you can really find a method in which you can take it out of the system. Talking yesterday with Dr. Jason Blackstock about geoengineering. There are other methods. See, all these are approaches one should look at. Even carbon capture and storage can be called geoengineering, in the sense that you kind of scrub out the carbon dioxide and take it away from the system. But the other people who are thinking that whether you can put, I was listening to Professor Richard Zaire from Stanford, sulfur dioxide into the stratosphere, so to reflect away a part of the sunlight. See, difference of what is coming and what is going is the problem. But these are all things which you have, of course, one paper, which I have to find out. Of course, this is, as I said, is only in the research and development stage. And if, so number of people are thinking very clever ideas. Then, of course, energy crops, and we must do more serious carbon balance studies. Should encourage production of algae which take away the carbon dioxide. Combustion research to do. So you talk of alternate fuels but use the same IC engine. Well, that's not the way. We should have combustion research. Look at the fast diagnostic, using fast diagnostics in order to see what's happening there. Then integrated gasification combined cycle, which we have done, because what works for low fly ash coal doesn't work for high fly ash coal. And then can you gasify underground itself? Because gas has greater efficiency production than coal. What we are thinking of is bringing these three large entities in India together. The Indira Gandhi Center for Atomic Research, which is really experts in materials, because when you go to high temperature, you have to look at things like high temperature corrosion, creep properties at these temperatures and so on. Equipment manufacturer like Bharat Heavy Electricals, the biggest energy infrastructure materials manufacturer, and NTPC, which is the biggest utility. And all of them will be doing R&D on their parts and linking them together with the National Knowledge Network. And we are also looking for international inputs in this mission, people who are working in this area. It's an extremely exciting R&D field. This is what my friend, Dr. Michael Monia from Sask Power sent me, carbon capture and storage. And they are leading the development of one of the world's first largest integrated clean coal carbon capture and sequestration demonstration projects. And as I said, it's unique in the sense that it's also used for oil recovery. Hopefully I'll be meeting him day after tomorrow. See, now various people have made various projections, and none of them is exactly the same. And particularly if you do global averaging, you may miss the detail which is relevant to each country or in fact each region. This is a projection by the International Energy Agency. And certainly the projection for nuclear for some of the developed countries will be, developing countries will be, in my opinion, much higher than this. This is from the European Climate Foundation. They have a roadmap, and what they say, well, as I said, whether it will come to pass, nobody can say. So they are assuming that Europe will cut carbon dioxide emissions by 80%. Will they? I'm not so sure. Will they, Dr. Jatwani? 80% by 2050. There are no symptoms of that. A major boost in the production of low carbon electricity. Here they are talking a mix of nuclear, carbon capture, fossil and renewables. And see, this is all based on assumptions that power demand 2050 40% higher than here. But this is the crucial statement, that of the three low carbon sources, none was found to be indispensable and none capable of meeting all power demand alone. So it depends on the way you see. There's a guy called, I think his name is Eaton, Vice President of Science and Technology of British Petroleum. He said each country will try to go for low cost, low carbon, and as far as possible local energy resource for their energy production. So the attitudes and approaches are going to be different. In nuclear, it will depend upon your technological infrastructure and the knowledge base and experience you have. Starting a new nuclear program suddenly, as my friend Director Bach was saying, the last country which started its nuclear power plant was China in '85. After that, nobody. It has increased in countries which already have nuclear power plants. The way they are doing the United Arab Emirates is something like the BOO, build and operate, not build and own, owned by UAE, but it will be operated, I think, 15 years by the South Koreans, because they don't have the manpower. You need trained manpower to operate this. And nobody is sure what will be the importance of shale gas, which has come in a big way in the United States and probably in other countries. Biofuels. I remember you were taking me to Iogen 5 years back. This is enzymatic ethanol. Of course, you don't want to take away corn and produce ethanol out of it and increase the prices, as they say, some people suspect happened. Prices of corn went up because you took it away for ethanol. Fusion may come, who knows? If fusion comes, these are all uncertainties. So on the other hand, we cannot take a risk, cannot wait for anything to happen. We'll have to assume that it is happening. Global warming has started. And in fact, as far as the developing countries are concerned, even if the climate change threat were not there, and if you look at the depletion of fossil fuels, maybe 40 years for 50 years for oil, 100 years plus for coal, whatever, you get the same answers: nuclear, renewables, efficiency, and hydro. And the longer you can keep your reserves of fossil, so much the better for the world. Actually the Indian intensity, what we call carbon dioxide intensity of emissions as given by GDP this parity corrected in terms of metric tons of carbon dioxide. Canada and India are pretty close. United States. Copenhagen, which didn't work out very well, the Copenhagen Accord, both Canada and India. Canada talks about emission reduction. India cannot talk about emission reduction. Where is it to reduce? Our production of power is so low. So what we are talking about is emission intensity reduction. That for the same amount of power, or we will produce less amount of carbon dioxide. As I said, Indian government, certainly Ministry of Environment and Forest, is getting very good data now, GHG emissions by the various sectors, so that one can take appropriate action. This was a statement made by our Prime Minister in 2007. See, the ultimate equity is equal per capita emission for every citizen of the world. Per capita emission is the only anyway inequitable parameter, because if you multiply per capita by the population of India, of course you will get a very large figure. That doesn't mean anything. Per capita. So what he says is, the next one countries in the Kyoto Protocol must come down. We will inevitably go up, because not working on poverty alleviation is not an option. But only thing we will guarantee you is we will go down together, we will not exceed you. That's why, let me give my energy security. When you talk about national security is not just military security. It also has food and nutritional security, environmental security, water security, and all that. Driving them all is energy security. And in this energy security, there's no doubt that we have to factor in. So this is my concluding slides: energy perspectives in the 21st century. 21st century is very difficult to see till the end of the century. Certainly we can see to the middle of the next century. Short-term perspectives, which is what you see around the world, depends upon the individual current levels of per capita energy consumption in every country. And least developed countries have a different, India is somewhere in between. My friend Hans Blix, when I used to say many years back, India is a developing country, he used to say, you are an advanced developing country. He used to say, you are a nuclear developed country. But of course we have to look at it as approaches of India and Canada will depend upon. Canada is a developed country, and the current energy mix, the locals' resources, the projected demand, and also available natural and human resources. The long-term perspectives, I think, I'm now going a bit beyond science. I'm going into territory in which I'm not an expert, but I think it will depend on the political perception and global peace and prosperity. I think excessive differentials in quality of life among countries may lead to conflict and instability. And I think all countries must work together in terms of what is known as enlightened self-interest, perhaps altruistic international collaboration. Altruistic. Now, I happened to be in Davos in 2008, and the theme of that meeting was collaborative innovation. Collaborative innovation. And that is increasing. There is companies across borders working together, sharing IPR. That is when I talked about altruistic collaborative innovation. There are some issues like climate change, or maybe if somebody has found a solution for climate change, at least mitigating a part of it or adapting to it. I mean, it's hardly fair that he holds it back for making money out of that. So I say you must have altruistic collaboration in this case, or you find something about an epidemic which is spreading very fast, you have a solution. And also related research and innovation. There's knowledge which exists, it should be shared. If knowledge doesn't exist, then we should collaborate in generating the necessary knowledge. That is why I think countries, at least countries which are enlightened, hopefully India and Canada among them, should collaborate to look at the problems in the fashion I have described. Now let me close with a slide which I took from Juser Wasi, Win, which is one of Professor Kati. He has large collaborations with Indian labs. One of them is IIT Bombay, and very interesting collaboration. And I'm sure that this is going to increase in the future. Many leading labs in India collaborating with leading labs in Canada. I'm now talking not related to climate change, but climate change should also can be a part of it. I think I'll stop here and thank you very much for your attention. Thank you.
Thank you, Dr. Chidabaram, for a very comprehensive sweep of the challenges related to energy, climate change, and the perspectives that you've shared with us, most enlightening, and some of your concluding slides, which are hopeful, as it were. We have time for, let's say, 10 or 15 minutes if you want to questions go. And my job is the easier one. I will be the traffic cop and direct the questions. I don't have to answer the question.
Comment on what we think a sustainable population goal would be. Everything we talked about hinges on population, obviously. Energy needs, everything. Effects on ecosystems, everything else. Loss of species is also affected in there. Water resources, all those things there. So simply having more electricity in the form of nuclear or whatever doesn't mean everything is solved. What do you think a sustainable population goal would be? I mean, if India, I think you said somewhere in there, India's carbon emissions are roughly similar to all of Canada, so India has far more people. So if India's goals of becoming first world living standard, like what we have here, even if it's carbon neutral, means all sorts of other problems. So can you comment maybe on what you think a sustainable population goal would be for?
You see, the growth rate is coming down, but hopefully it will not go very much higher than it is going to increase. It's not going to stay at 1.2 billion. But very interestingly, this even though the population of India has grown, the demographic distribution has gone favorable to India. There are many countries now in which the population which has to be supported and the population which is creating the wealth, that ratio is going very unfavorable at the moment. So that doesn't mean we can continue to grow like this. But it is coming down, that's all one can say. I have not studied this issue in too much detail.
If I may add to the question, perspective on a global perspective, look at United Nations demographic projection for global population growth. It reaches stationarity around 9 billion, 8.79, 9.2, down the early 20s. So the world population, with or without any population policy, explicit or otherwise, will reach stationarity around 9 billion. The world will go to around 9 billion in stability. And if you want to know why, there's a vast amount of literature in demographics that supports that position. Whether it lands at 9.5 or 10, it will not continue to grow according to Malthusian type of propositions. So that there is that. In countries it will vary.
May I add something to this? It also depends upon literacy and prosperity.
Absolutely.
If you have a high prosperity and high literacy, population will automatically get controlled. You know, correlation.
I think you are right. Female literacy particularly correlates very strongly with birth rate, even among Indian states.
I was wondering if you could comment on plans for development of training programs for careers in this type of sustainable energy technology.
Sorry, I'm not able to hear.
Sorry. I was wondering if you could comment on plans for development of training programs in India for careers in sustainable technology.
What program? Training program?
Just like the plans for development throughout the country for training programs for careers in these technologies.
See, of course, there are several kinds of things. You know, if we take nuclear energy itself, we have had one of the best programs is the training school in the Bhabha Atomic Research Center. We used to take about 150, 200 people. It's going on from 1957, and then train them physics and chemistry and mechanical engineering and all that. That number has now grown. Nuclear Power Corporation has its own program, Indira Gandhi. Maybe 500 people are coming out every year. And the applicants for this are maybe 20 times the number who are finally selected. And then one of our best institutions are the IITs. That's for a more general terms of education. And what the government has done is to start half a dozen new IITs which are taken. See, the more serious issue is in basic sciences. See, basic sciences after the 12th standard, we find that people who should be doing pure science are going in for professional courses because they see better career prospects over there. And for that the government has started five Indian Institute of Science, Education and Research, which give 5-year integrated MSc courses, and some of them can go on to PhD later. So there is a very deep concern that particularly in basic sciences one should grow more people. Because the alternate careers available now have become attractive careers. The people who earlier on were going into science or research are now drifting into these other careers.
Thank you for your talk. It was very informative. I guess my question is related to the, is it, given that the government of India is really thinking very seriously about growing and economically, while taking into account the threat of climate change, and you guys have a mission for energy security and education, all of that. Do you think that there is another parallel effort to take into account the environmental implication of growing economically? Or
Environmental?
Yes, like environmental protection agencies, if you can comment on that, what type of effort are you doing to basically monitor and also to maintain the natural habitats of species near the areas that you are going to develop?
See, all the things which you are saying we are trying to do, but poverty alleviation has to be the primary concern. And very often what it happens is, particularly in adaptation strategies, that the programs that you have to do, which I have not discussed here, for adaptation strategies are exactly the ones you should do for poverty alleviation. For example, you talk about the sea level rise. The sea level rise will inundate low-lying areas. But if you find in any urban conglomerate that the low-lying areas are occupied by poor people, the rich guy lives up the hill, he is not affected. What the climate change does is to increase the frequency and intensity of these extreme events. By and large, it doesn't produce anything new, but the frequency and the severity of those events. So the low-lying areas are going to get flooded. Suppose as part of our alleviation program, poverty, if you take care of that, automatically you are taking care of the climate change thing. And of course, environment, as Indira Gandhi once said, Poverty is the greatest environmental pollutant, poverty. So you have to take care of the local pollution, you have to take care of the regional pollution, and then also you worry about the global environmental effect.
I guess my concern is because of the fact that, you know, the definition of not being poor is usually, you know, proportional to consume more. So you're not really, you know, you could be rich, but at the same time your consumption increases and your impact on the environment could be, you know, even worse than a poor person who's really that, you know, is poor and conserves and recycles and all of that. You see what I'm trying to say here?
So all of us have to be, this is why the Kyoto Protocol says all of us have responsibilities which are common but which are differentiated. Common but differentiated responsibility. Reinforced in Bali, well, kind of let loose in Copenhagen. This is the problem.
Let's take the last question here. Thank you. One more to go.
Given the central position of energy storage, whether the final energy scenario is based on nuclear or on the photovoltaic scenario, the countries like US, Germany, and Britain now have central schemes connecting to physics and materials research to the battery storage and other related storage. I want to know if there is any scheme for India.
See, there are programs on energy storage. In fact, in our steering committee report for the 11th plan, we talked also of batteries and ultra capacitors and all that for, but they are not as big as the programs that you have even here and in the United States. It's the problem. They are, say, lithium-ion batteries, where we had an excellent program which is going on, which has got applications in other areas beyond energy storage for power. So these are all things which we have to watch and do. They are very important areas.
Okay, thank you very much for your questions, and I'd like to remind you that there is a reception in